Section 12.4, we're taking a look at tangent vectors and normal vectors, and I'd like to sort of motivate the point of what this section is about to start with. So if you're designing roads, you would like to avoid curves that are too sharp, correct? Yes. We're not talking about roller coasters, we're talking about roads. Roads. In this section and in 12.5, we're going to develop a measure of how much a curve is twisting or turning at any point. Okay? So that's what we're going to be looking at, is the twists and turns values kind of for curves. So you can think roads, you can think roller coasters. I mean, like the same would be true to some degree for the roller coasters. It might be a little bit more daring, but there's still a level at which you don't want the people falling off. The answer is yes, Connor. We don't want the people falling off. Adrian?
So it's actually a question on our scheduling, because I was looking at when I printed this out. I only saw 12.4.
Yeah.
So
12.5 is there. It got shifted to lower because there's actually section 10.5 I want to do before we do 12.5. When I teach these next time, I'm going to flip some things around, but it just got shifted. The test hasn't changed.
So is that going to be over 12?
10 and 12. 10 and 12 are both on the same test.
Okay, that's what I was trying to figure out.
Yeah.
Like you don't have a test next
No,
week. But
10 and 12 are the same test. Again, that's a new thing. We'll see how it goes. You guys are my guinea pigs a little bit. I haven't done a test like that before. But when I pulled 10.4 out of chapter 10 and put it inside of chapter 12, remember we did that? With the polar stuff that we just did? It made 10 and 12 about the same length as you get chapter 9 to be. And so I felt like it was probably reasonable that we made 3 tests instead of 4 tests. And nobody complained. Because 3 tests.
We have a better chance of getting better test grades.
Perhaps.
After 10, we just have 9. That's it for 12.3.
Mm-hmm.
That's going to be like the majority of the
Chapter 9 is really long.
Yeah, that's like the next half of the semester.
Yeah.
Okay.
So is 10.4 still going to be?
No, 10.4 won't be on this next test. We already did it, so yeah.
Okay.
All right, so this measure that we're talking about is the unit tangent vector, and then we'll encounter something else in section 12.5 that addresses some of this issue. But the unit tangent vector is calculated by finding the derivative of position, right? That was velocity, so r prime of t, and then dividing it by its magnitude. Okay, so this is the velocity equation turned into a unit vector, correct? That's what this is, because r prime is velocity. So we should do an example and see how this works. So the first thing we're going to do here is we're going to find the unit tangent vector, part A. And then B is we're going to find a set of parametric equations for the line tangent to the curve at t. So I'll dabble a little bit in the parametric equation part of this. It's not going to be too bad. We haven't talked specifically about parametric equations, which is inside of chapter 10. Like I said, when we do this again, 10 and 12 are just flopping places, and I think it'll work a little bit better. But let's start with A. A is something we've definitely done and we can handle just fine. Okay? So here's the way that this is going to work. R prime of t to start with. And this one is just 2 components. So what's the derivative of 3 cosine t? Yep, derivatives. Okay, so negative 3 sine of t. Good. And then the derivative of 2 sine t? 2 cosine t. And we're supposed to be evaluating this at a particular point, pi over 4. Okay, so we're going to evaluate at pi over 4. So negative 3 sine pi over 4 and 2 cosine of pi over 4. And what is the sine and the cosine of pi over 4? Yep, square root 2 over 2. So this first one is negative 3 square root 2 over 2. And then the second one would actually just be square root 2. Okay, is that okay? Everybody good so far? Okay, what these are going to do, I'm going to just mention it right now, and then we're going to finish the part A of the problem, is that these 2 values are going to give us some slope values, which should not surprise you because derivatives give us slopes, right? They're a slope of something. So keep in mind this is going to have something to do with the slopes of these parametric equations that I'm going to talk about later, okay? All right, the second part of part A then is finding the magnitude of this. So we need to find the magnitude of this at pi over 4. So we'll have the square root of each of these squared. So I have negative 3 square root 2 over 2 squared and square root 2 squared. All right, so I'm going to have 9 times 2 over 4 and 2 that look okay? 9 times 2 over 4 would just be 9 over 2. And plus 2 would give me what? What is it? 13. So it's 13 over 2, right? And if we wanted to rationalize, which we will when we have a denominator that's a value that's a number, right, not a variable, this would be square root 13 over 2 with a 2 in front. Let me just make mention of what I just did. All I did was multiply by square root 2 on the top and bottom. On the bottom, the square root 2 came out. I should say square root 26 on the top. Sorry, I put it in the wrong spot. 26. So square root 2 goes underneath the 13 on top, so square root 26, and then I have 2 on bottom. So then if I'm trying to find my unit tangent vector, let me shrink this so I have a little bit more space. I'm almost done with this part. The unit tangent vector then, t of t, is going to be each of those individual pieces, which had 2 of them, divided by the magnitude. So we had negative 3 sine pi over 4 divided by square root 26 over 2. And we have 2 cosine pi over 4. Oh, I'm sorry. I don't know why I'm writing it that way. I don't want it. How do I want it written? Generically or with the values put in? With the values put in. So let's just put this back in there. This was square root 3, or 3 square root 2 over 2. There we go. Pulled up in the wrong spot. Square root 2, and then it's divided by the square root of 26 over 2. Okay, so that looks awful. We definitely should not leave it like that. It looks terrible. So if I flip and multiply, these 2's are going to cancel at least in the first one, so that's nice. I'm going to have negative 3 square root 2 over square root 26. If I rationalize, that'll clean that up a little bit, actually. So we have, let me see where we are right now. I have negative 3 square root 2 over square root 26. And on the other one, I have 2 square root 2 over square root 26. Does that look like what you guys have? I have all these details written in my notes, but let's just check. Looks like, good. The parts that actually can simplify underneath the radical, we can do that, and then we can rationalize. So this 2 underneath the radical beside the 3 with the 26, they're both underneath radicals. I can simplify 2 of those 2's. So this square root 2 actually will completely cancel out with this 26, leaving me with 13 there. And this square root 2 will cancel out with this 26. Whoops, leaving me with a 13 there. Now the 13's are still underneath the radicals, but they're still there. And once again, I'm out of space. Now we're going to rationalize, yep. All right, so we have negative 3 square root 13 over 13 and 2 square root 13 over 13. Right, so they're ugly, right? Yeah. These are ugly values. It's an exercise in algebra, the majority of the problem, correct? A little bit of trig in there, tiny bit of calculus at the beginning, but a lot of algebra. All right, so you're ready to take a look then at what we're going to do for this tangent, parametric equations part for the tangent stuff, okay? Okay, so what parametric equations are, in brief, is we're creating a expression for how something changes in terms of its x value, its y value, and if we had it, its z value, as well as some other parameter changes. And that parameter is typically time, so you see t used a lot. So if t is time, something's changing in respect to the x-axis, right? The x values are changing in a certain way with respect to time. The y values are changing in a certain way with respect to time. And then z if we were doing it with z. So that's in a nutshell what we're doing. And so here's the way it's going to work. We're going to let our x value be represented as a linear equation. Now, what is a linear equation that you guys know? Don't ignore my x equals for the moment. What's the general linear equation? Yeah, y equal mx plus b. Everybody with that, right? So our general linear equation, the slope-intercept form of a line that you're most familiar with, looks like y equal ms plus b, right? We use it a lot. We're using this form for your equations for x and for y. Okay, that's what we're going to do. I don't want it to say m, and I don't want it to just say b, though. All right, so y equal mx plus b, I want to make sure that I understand that the m and the b can be different, right? I've got two equations. One's going to be reflective of what's happening in x, and one's going to be reflective of what's happening in the variable y. So the way that I'm going to represent them to get them to look different is that these are going to be equations for x and y, is that I'm going to write them as x1 plus at and y1 plus bt. So the x1 and the y1 are acting like your intercept, right, b. That's the b value. And then the a and the b in this right here are acting as slope. And the slopes potentially are different. Everybody good so far? All right, we actually already have the slopes. We got them from the original derivative equation that we had. So if you come back over here, these slopes right here are what we're going to be using for the a and the b. So the first one in the I location is the A, because it's going to go correspond with the X coordinate, right? And the second one's going to correspond with the Y coordinate or the J component, okay? So this one right here is going to be A, and this one right here is going to be B. So over here, we already know that my A value is negative 3 square root 2 over 2. And we already know that our B value is square root 2. Okay, everybody good so far? We still need a point. Like we need an ordered pair. I need a location for an x1 and a y1 on this curve. And technically, I want to find it at that same point that I already have. My value is at pi over 4. Okay? So what we're going to do is we're going to actually find out what is r of pi over 4. Because that location provides us with a point on our curve. Correct? So we're going to put pi over 4 in for each of those values in the original vector valued function we have above. So 3 cosine of pi over 4 and 2 sine of pi over 4. All right, so we already did cosine pi over 4 and sine pi over 4. Those are the square root 2 over 2's. So this one is 3 square root 2 over 2. And this one ends up actually giving us another square root 2. Okay, all good? Okay, so these values are x1 and y1. So we can actually put these into this equation just like we're going to put the x and the y equations, just like we're going to put the a and the b in. So this right here will become x equals, the x value is 3 square root 2 over 2, and then plus my a value, which is actually negative, so minus 3 square root 2 over 2t. And then the y value is the y1, which is square root of 2, plus the b value, which is another square root of 2t. And these are the parametric equations that will do this for us. And the pattern will be the same for all that we're working with. We'll develop more about parametric equations in other contexts later. Okay, but they're going to work like this for what we're doing in this section. All right, ready to take a look at the other piece in this section?
So that's the end there, so that's the lines tangent to the curve at t?
In parametric form.
Parametric.
Yes, these are the lines tangent to the curve in parametric form.
And what does parametric mean exactly again?
It means that we're deciding what the x and the y values, or z as well, are in terms of some other parameter, and typically that parameter is time.
Okay.
So as time changes, how are the x values being affected? As time changes, how are the y values being affected?
Okay.
Yep.
Makes sense. Thank you.
Okay, so far we've written all of our vectors in terms of the standard unit basis, I, j, k. True? Yes, we've done that. Sometimes other choices are convenient. For example, for an aircraft in flight, a better frame of reference would be one that moves with the aircraft. Okay? So what we're going to do next is we're going to create what's called the principal unit normal vector, n of t. It's another unit vector. It's a unit vector having the same direction as t prime. We just found t a minute ago, right? Capital T, we found that. It will be the same direction as the derivative of that, and then turned into a unit vector. This is a principal unit normal vector.
Because we're really far down the derivative rabbit hole now.
Yeah, we just keep going on the derivatives. Okay. Now, I think I should probably go back just a second and make a mention of what we're going to have to deal with now that we didn't have to deal with before. On this previous problem, we were able to substitute in pi over 4 pretty quickly, correct? It was very nice in some sense because it was a nice value that we're familiar with. But we did it before we found the magnitude, right? And you guys encountered this on the boards one day when you were working with some problems where you were evaluating things in certain cases too soon. Now, there's nothing we did wrong here. The problem, however, is that if I want to take the derivative, I actually wrote this in a way that's probably not real helpful. It's fine for now. If I want to take the derivative of this t prime of t, like if I want to take the derivative of this one right here is not what I want to take the derivative of. Because what's the derivative of this? It's 0, 0. Are you with me? Okay. What I want to take the derivative of is what it would have been if I had never plugged pi over 4 in. Well, that's fine. I mean, we did it without the pi over 4 plugged in. It was the very original thing, so there's nothing wrong with that. But we would want to actually find the magnitude of that general equation to finish it out instead of finding the magnitude of the value of the one where we plugged the value in. Okay, are you with me? So what we could have done on this problem, we didn't, but what we could have done is from this point right here, we could have found the magnitude at this point. Right? And if we found that magnitude, we could have used that quantity, which would still have variables in it, right? To divide the original r prime of t equation. We could have done that, and that would have been an arbitrary quantity instead of an evaluated up to pi over 4 quantity. So as we're taking a look at this next problem, which looks like a lot of the same things we're dealing with, right? We've got sines and cosines showing up. What we're wanting to do is we're wanting to do it generically because we're going to take a derivative again after we did what we did last time. So the question first says, find the unit tangent vector, and then part B says to find a principal normal vector at the given point. Okay, so first things first, we're going to find r prime of t. All right, so derivative of 2 cosine t, negative 2 sine t, derivative of 3 sine t, 3 cosine t. Now, eventually, I'm going to need to actually have this in terms of t. So the next step that I'm going to do right now is going to be to find r prime of t's magnitude. So I'm doing it generically. So I have negative 2 sine of t squared plus 3 sine of t squared. I know everybody's wishing their coefficients weren't there, right?
3 cosine of t squared?
Yes, I do. Typo, thank you. Here we go. So again, if the 2 and the 3 weren't there, it would be much nicer. Agreed? We'd have a Pythagorean identity we could apply and so forth. We're still going to apply it. It's just not going to be quite as friendly to condense things. So let's see what we have. Well, this gives me 4 sine squared t plus 9 cosine squared t. True? Excellent. Now, it won't just zap each other out, right? It doesn't disappear into 1 or some other constant number, but we can break it apart so that it would be able to be replaced in part by a constant. So in particular, this one says 4 sine squared t. And if I had a 4 cosine squared t that I added to that, those two would equal the number 4, right? Because sine squared plus cosine squared equals 4. So what I'm going to do, and I'll do it right here, and if I need to erase it, I will, for the sake of time or space. So this is 4 sine squared t plus 4 cosine squared t. And I still have 5 more of them, agreed? 5 cosine squared t. And these two right here can combine, whoops, and they equal the number 4. Sine squared plus cosine squared equals 1, and then when I've got a 4 in front of both of them, they're going to equal 4. So this piece right here will become simply the square root of 4 plus 5 cosine squared t. And that is as good as it's going to get. There's not a nicer way to actually simplify or change this in any other form. This is it. So when I'm finding my unit tangent vector, I'm finding this t value where it takes the r prime of t that I started with, right? My first thing I found, negative 2 sine t, 3 cosine t, and divides it by this quantity in radical form. I don't have to simplify the radical, though, in the denominator, right? I don't need to do that, but that's what I would have. So I'm going to have negative 2 sine t, and it's going to be over the square root of 4 plus 5 cosine t. So it's cosine squared t. And then I'm going to have 3 cosine t. And it also will be over that same square root, 4 plus 5 cosine squared t. Okay, we needed to do that generically because on part B, what we're going to be doing, actually let me flip it back one, is we're going to be finding the magnitude, well, we're going to be finding the derivative of what we just found, which is going to be ugly because now I have a quotient rule, right? It's not going to be pretty. And I'm going to have to find the magnitude. Now the magnitude part down here is not going to be as bad because I will have evaluated at that point. I can simplify some of the mess, but the derivative part's going to be messy.
This looks nasty.
But I'm not done, okay? This part of the problem still does want me to evaluate it at pi over 4, whatever I've got. What is it? 0. It still wants me to evaluate it at 0. I just need to evaluate it at 0 here instead of earlier than here because I will never get to here if I evaluate it too soon. Is everybody with me? So I am still going to evaluate this. I am still going to find t of 0. Okay, I'm still going to do that, but I'm going to do this from the very ending part where I just came to. Okay? So I'm putting 0 in for each of the t's in this expression that I just got. So some of those are going to 0 out. Some of those are going to become 1s and other numbers, and that's going to be very nice. All of it needs to be shifted over because I'm running space.
Evaluate it.
Do you have to find the derivative first to evaluate it?
Shouldn't be t prime of t before we evaluate at 0?
We will when we get to finding the normal vector. We're not there yet.
Oh.
Right now we're just finding this one right here. We're just finding t of t. Okay, right now we're still just finding t of t. Or, well, t of 0. Not t prime yet. Okay, so for these, I'm going to 0 some things out. So this is going to be negative 3 sine t. What is sine 0? What is sine of 0? 0. So it doesn't matter what in the world happens down here, right? It's 0 on that first term. That's fantastic. Okay, the next one. Well, it's not 0 because it's cosine. So it's 3 cosine of 0. What's cosine of 0? That one's 1. So I don't have it quite as friendly on the second one. But this piece is also going to be cosine of 0 underneath the denominator, right? So I have a 4 plus 5 times 1. So what's that denominator end up being? A 3. So this is, because this is 9 underneath, I take the square root. So this is 3 over 3 or 1. So the tangent vector that I was looking for, right, t of 0 is actually 0, 1 in the direction, or when at the value t equals 0. But again, if I did all this and then I try to take the derivative of 0, 0, that doesn't help me. I don't have a variable in it to actually find how things are changing again, or still. Okay, this, however, where I have this down here, I need for my next slide. So I'm going to copy it. And we're going to put it over here. Okay, so this is where we've left off from the previous problem in finding these. And what we're at right now is that I need to find t prime. And it's going to be very long. I should probably even already, I should just leave the A's and B's off these screens. So ignore the fact that I'm right on top of the letter B. It's just going to be long. Okay, so each of these are going to have a quotient rule, correct? And the derivative of the denominator, or we can change it into a product rule if you wish. The derivative of the denominator itself is also going to have a chain rule. And not only is it going to have one chain rule, I think it's going to have two chain rules because we have another embedded function underneath the radical. This is a messy problem, right? Let's do it as a quotient rule, because that's what's in my notes. And that way, if I need to check something and see if I mess something up, I've got them. But understand that if you wanted to pull the denominators up and make them a negative 1/2 power as a product rule, that would be okay too. All right? So, we're all glad that we've worked on derivatives and antiderivatives in my office lately, right? I hope so. I hope it's helpful. Well, we're about to find out.
Would it be faster the product rule or the?
It's about the same. Yeah, it's about the same. The denominator squared is actually really nice, though. So when I do the quotient rule here and I do the denominator squared, that's going to be lovely because I just need this, right? So that's going to be great on both terms. Let me just start with the first one. All right, so the first one, the I component, I need to do low d high. So the denominator first, low, is 4 plus 5 cosine squared t underneath the radical times the derivative of what's on top. So what's the derivative of negative 2 sine t? Don't everybody say anything at once. What's the derivative of negative 2 sine t? Thank you. Negative 2 sine t. Cosine t. You said cosine and then I still wrote it wrong. Cosine t. Okay. That's half of my derivative on top, right? Or that's half of the top when I'm doing my derivative. It's the easier half. So now then we're going to write the numerator, which was negative 2 sine t, and we need the derivative of the denominator. So the derivative of the denominator, what's that? Oh, I put my subtraction sign there, didn't I? Or my addition sign instead of subtraction sign. There we go. Thank you. All right, so on the second part then, I need the derivative of the denominator. Well, it's underneath a radical, so I'm going to write down that I've got a 1/2, right? So the 1/2 comes to the front. I'm going to rewrite it, so that's 4 plus 5 cosine squared of t. And then I'm going to have, the exponent, negative 1/2. And then I need the derivative of 4 plus 5 cosine squared t. Well, the derivative of the 4 plus part, that's 0. What's the derivative of the 5 cosine squared of t? It's 2 to make it 10, right? The 2 is going to come down with the 5 to make it a 10. And then it's going to say cosine of t to the power, like we've got cosine of the 1, right, of t. But then I need the derivative of cosine, which is negative sine. I'm going to put the negative in front of the 10 so that I'm not embedding too many parentheses here. Now, I have limited space on my screen, but I am at the end of my screen, and that's one of the two derivatives. The kicker is that the other derivative is similar, right? The j component's almost the same thing, at least on the parts it's hard. Okay, so let's do the j component then. Okay, so that's our first one. We have a comma down here that looks like it's out in the middle of nowhere, but it's not. Now we need to do the second one. Well, it'll have the same denominator. It's 4 plus 5 cosine squared of t. Okay, and we're going to do the denominator times the derivative of the numerator. So what's the derivative of 3 cosine t? Negative 3 sine t. We'll get the subtraction sign in this time. And then I need the original, so that's 3 cosine t. And then I have all of this right here from the 1/2 over is the same because it's the derivative of the same denominator, right? The denominators match on this particular one. So this actually at the end is exactly the same. I don't know if I can copy it, but we'll try it. There. So all that's the same. I'm a little bit off screen. Here we go. Isn't that fun? Okay, we're going to clean it up a little bit, but we're really going to be plugging 0 in very soon. Agreed?
Yeah.
Okay, so if you don't want to clean it up at all and you just want to plug 0 in right now, you could do that and it'd be okay. I think we can clean up a little bit of stuff maybe. No, I don't. I didn't clean up anything. I think I just put in zeros. You good with that?
Yes.
Okay, let's do it. So we're going to find t prime of 0. And we're going to move from left to right. So we already know that all of those square roots are going to become 3s, right? The square root has a 4 plus 5, the cosine squared, right? The cosine squared is going to be the value 1. So all of the places where I have square roots are actually the value 3.
Isn't the whole thing 0?
I don't think so. Nope, it's definitely not. All right, so this piece right here is 3. Do you mean the first part or the second part? One part is 0, but not the whole thing is 0. So I've got a 3 times. What is 2 cosine of 0? Negative 2 cosine of 0? That one's negative 2. All right. And then we have minus, I have a sine of, this 2 sine of 0. That's 0, and that's going to 0 everything else in the numerator out, right?
Yeah, that's what I was.
That's going to give you a 0. So this piece is 0. That's nice. The denominator is going to be what? 9. Whoops. Get my tool back up. 9. Second denominator is also a 9. So let's see what happens. I have a 3 again. But on this one, I have negative 3 sine of 0. So this is actually my 0 on this one, right? The other one's not going to necessarily do that for us. So we have on the second one, this 3 cosine 0, that's going to be 3. This 1/2 is going to stay. This piece right here is going to be 3, but it's going to be in the denominator, right? Because it's got a negative power. So this is 1/3. But what happens over here? That's my 0. So the entire numerator of the second piece is going to be 0. Okay? So the first one, I end up getting negative 6 over 9, right? Well, I'll write it first that way. Negative 6 over 9. The second one is 0. And what do I get when I take negative 6 over 9 and simplify? Yeah, negative 2/3. Now we're still not done. We're done with half. So this is negative 2/3, 0. But we are definitely done with anything hard.
Yeah, there we just.
The magnitude for the next piece is not hard. So let me actually write this down that we did this. Move it to the next screen. Okay, we need to find the magnitude of this one now, right? So what's the magnitude of t prime of 0? It is 2/3, right? And we know easily because it's only got one component. If you wanted to square it and square root and so forth, you'd still find the same thing. It is 2/3. And then if I want to find the normal vector, which is what I'm looking for, it will be that t prime vector divided by its magnitude. All of this shouldn't be at t, it should be at 0. My apologies. There we go. And that is our vector negative 2/3, 0, divided by 2/3, which gives us what? Negative 1, 0. So the two that we did ended up giving us vectors at the end that were 0 in one component, so it makes sense that they're a 1 or a negative 1 in the other component. That doesn't always happen. And I wanted to make the fix. I noticed it when I was doing it, but I didn't want to do it right then. On problem 1 over here, was it 1A? Yeah. This one right here that we did was not t prime, not t of t, it was t of pi over 4. Because we had plugged pi over 4 in at the point when we did that. So that was actually supposed to be t of pi over 4. Okay. We're going to stop there.